At the beginning of my talk, I want to appreciate help of Professor Gavrilchenko at Odessa University, under whose supervision I wrote my diploma research paper, Linear Representation of Lie Group. Almost 50 years have passed since then. I am glad that at the next turn of my research, I return to this topic, but already in non-commutative algebra. We start from definition of linear map of associative algebra. Let A be associative algebra and Z be center of algebra A. Linear map of algebra A is linear map of Z module A. We use notation 2.1 for image of linear map F. Let F be linear map of the algebra A. Then maps AF defined by quality 2.2 and FB defined by quality 2.3 are linear maps as well. From this statement, it follows that for any linear map F and any tensor A times B, the map 2.4 divided by quality 2.5 is linear map as well. And tensor F from tensor square of algebra A has a representation 2.6, where a number f is 0, f is 1 are called components of tensor. In the equality to the 6, I use convention similar to Einstein's convention. If index is repeated in components of tensor, then corresponding expression is sum over this index, and the set of values of the index is finite. However, this set depends on the tensor. According to this convention, the expression 2.6 is equivalent to the expression 2.7. This convention allows us to avoid excessive use of summation symbol in complex expressions. For instance, you can compare left and right side of the equality 2.8. Because sum of linear maps is linear map, then the definition of linear map 2.5 can be extended to any tensor 2.6 using equality 2.9. If we introduce product to the 10 on the tensor square of algebra A, then tensor square of algebra A is the algebra, and the set of linear maps is left module over tensor square of algebra A. If the algebra A has finite dimension, then module of linear maps has finite dimension as well. In particular, if module of linear maps has dimension 1, then we can identify linear map to 11 and tensor F from tensor square of algebra A. The representation 2.6 of the tensor F is ambiguous. For instance, you can see different representation of the same tensor from tensor square of algebra A. If you consider the basis E of the algebra A, then the representation 215 of the tensor F is uniquely defined and is called standard representation of tensor F. The numbers Fij are called standard components of tensor F. In the equality 215, I use Einstein's summation convention in which repeated index, one above and one below, implies summation with respect to repeated index. A matrix whose entries are linear maps is called matrix of maps. You consider following operation on the set of matrix of maps. Addition is defined and revised. A row column product of matrix of maps is defined as product of row of matrix F over columns of the matrix G. An entry of product is superposition of map Fki and GIL with following sum by index I. Row column product of matrix map of cones of n numbers is defined as product of row of matrix F or cones of matrix V. An entry of product is image of a number Vi with respect to the map Fki with following sum over index I. Column row product of matrix of maps is defined as product of columns of matrix F over row of matrix G. An entry of product is superposition of maps FIL and GKI over index I. Column row product of matrix of maps and row of A numbers is defined as product of columns of matrix F over row V, and entry of product is image of a number Vi with respect to the map Fik with following sum by index I. Now we're ready to consider calculus. The map F of Banach module A into Banach module B with corresponding norms is called differentiable on the set U if at entry point x in U, the increment of the map F can be represented as inequality for that one, where the F over the X is linear map of the module A into the module B, and O is such continuous map that it has norm 0 equality for the two. The linear map F over the X is called derivative of map F, and the differential the F of the map F is defined by equality for that free, where the X is differential of the argument. This definition is equivalent to the definition for that 4, where T is a real number. From this definition it follows the derivative of identity map is the identity map equality for that 5. Derivative of linear map is linear map itself. Derivative of x squared defined by equality for that 7. And derivative of x cubed defined by equality for 11. Let f and g be differentiable maps of the algebra A into Banach the algebra B. The derivative satisfies to equality for 15. Let A be Banach the module and B and C be Banach the algebras. Let f and g be differentiable maps from the module A into algebra B and C. The derivative satisfies to equality for 14. Let A be Banach algebra and f and g be differentiable map of algebra A into tensor square of algebra A. Derivative satisfies to equality for 15. Difference of equality for 15 from chain rule is due to the statement that the range of the map F is subset of tensor square of algebra A, not the algebra A itself. Now, let V and W be Banach and models of columns. Let EV be a basis of left and model V. Let us represent the number the X as column vector for 16. Let EW be basis of left and model W. Then the derivative of the map F from the model V to the model W as representation for 17 relative to selected basis. Yes, this matrix is Jacobian of the derivative. Let E be basis of Banach model V. Let partial derivative of map F be continuous and differentiable on the set U Let mixed partial derivatives of second order be continuous on the set U. Then on the set U, mixed partial derivative satisfy equality for 18. Now we are ready to consider differential geometry. Let B be Banach algebra and M be topological space. If there exists homeomorphism F of topological space M in the convex set N of the space B in power N, then homeomorphism F is called chart of the set M. Remark: if the map F is the chart of the set M, then for any point M in M, there exists tuple M1 Mn of B numbers which uniquely defines the point M. Another remark: if there exist two charts F1 and F2, then the map F on continuous diagram 5.1 is homeomorphism. We can represent homeomorphism F a system of equality 5.2, where x1, xn belongs to n1, y1, yn belongs to n2. If map f1, fn has derivative of order k, then the map F is called diffeomorphism of class Ck. Definition: let B be Banach algebra. The set M is called simple B-manifold of class Ck if for any two charts F1, F2, the map F on commutative diagram 5.1 is diffeomorphism of class Ck. Another definition: topological space M is called differential B-manifold of class Ck if topological space is a union of simple B-manifolds Mi, an intersection of simple B-manifolds Mi, Mj is also simple B-manifold. Two-dimensional sphere is the simplest example of non-trivial differential manifold. There is no homeomorphism mapping sphere to a plane. However, we can consider sphere as a union of two hemispheres. For instance, union of northern hemisphere and southern. We also assume that both hemispheres have a common strip along the equator. Telegraphic projection 5.3 is the diffeomorphism of hemisphere to plane. In commutative algebra, we define vector which is tangent to manifold according to law of transformation of coordinates of vector when we change basis. In non-commutative algebra, this definition is unsatisfactory because in non-commutative algebra, there is difference between homomorphism and linear map. In non-commutative algebra, we also identify vector and differentiation. This definition is equivalent to one discussed above. We can consider a similar definition in non-commutative algebra. So, let M be differential B-manifold. Let U be chart of manifold M such that X belongs to U. Let B manifold TXM generated by a set of partial derivatives 6.1 at point X is called tangent space. The set of partial derivatives 6.1 form basis of tangent space TXM, and we call this basis the coordinate basis. In commutative algebra, linear combination of differentiations is differentiation. In non-commutative algebra, the statement is false, as false from the equality 6.2, because AF not equal FA. However, V elements of tangent space or vectors or differentiation. If we at every point X of chart U choose a basis EX of tangent space XM, and coordinate of basis EX with respect to coordinate basis are differentiable map of point M, the set of bases 6.3 is called reference frame of manifold M in chart U, or just a reference frame. If at every point x in U, basis EX is coordinate basis, then reference frame E is called coordinate reference frame. Let basis EX has coordinate 6.4 with respect to coordinate basis, and holonomic object is defined by equality 6.5. If an holonomic object is 0, then there exists chart U on manifold M, in which the reference frame is coordinate reference frame. Now we consider lead derivative. The map 7.1 of point of manifold M into tangent space at point X is called vector field on manifold M. Vector field 7.2 on manifold generates infinitesimal transformation 7.3, where epsilon is a real number. Infinitesimal transformation 7.3 generates linear map 7.4 of tangent space Txm into tangent space Tx plus V at f of M. Let 7.5 be another vector field. From equality 7.4, it follows that vector field W is transformed according to the equality 7.6. Since vector field W is differentiable, then equality 7.7 follows from definition of derivative. According to the definition of free derivative, we have equality 7.9, which follows from equality 7.8. In commutative algebra, lead derivative of vector field coincide with their commutator. So we consider also commutator of vector fields. Commutator of vector fields A.1 and A.2 is defined by equality A.3. From this equality follows equality A.5. Therefore, commutator of vector fields A.5 similar to the lead derivative 7.9. However, the order of factors is different, and commutator of vector fields is not vector field. Now we are ready to consider Lie group. Let B be associative algebra. Let differential be manifold G be multiplicative group with product 9.1. Let map 9.2 be continuous map of class C2. Differential be manifold G is called Lie group. If we consider chart of the manifold G, then map that 9.1 is equivalent to the set of maps 9.3. We may consider left and right shift on the Lie group. However, the equalities and definition are similar, so we just consider left shift. Derivative of left shift AL is defined by equality 9.4 and is a linear map, which maps tangent space TAG of B manifold G into tangent space TBA-G. We may consider maps AL as entries of Jacobian matrix of left shift. If algebra A is commutative, then entry belongs to algebra A. If algebra A is non-commutative, then entries belong to tensor square of algebra A. We introduce Lie group basic maps 9.10. By definition, basic maps linearly map the tangent space TEG to the tangent space TAG. In particular, basic map at points E is a density map. Because basic maps has inverse map, we introduce maps lambda by equality 914. In particular, maps AL has representation 916. Theorem. Lie group operation satisfy the differential equation 918. For left shift tended 1, the system of differential equation 918 get form tended 2. The equality tended 5 follows from definition of integrability of system differential equation tended 2. Right side of equation equality tended 5 does not depend on C. Therefore, we can assume that expression tended 6 does not depend on C. The equality tended 7 follows from the equality tended 6. For any vector 1016, vector field 1017 is called left invariant vector field because left shift does not change this vector field. Let V and W be left invariant vector fields. The derivative 1018 follows from the definition 709. The equality 1019 follows from the equalities 10.7 and 1018. Therefore, vector field 1020 is left invariant vector field generated by vectors 1021. Binary operation 1021 is product in module T и G. Module T и G equipped with product 1021 is called Lie algebra GL of Lie group, and tensor 10.6 is called structure constant of Lie algebra GL. Thank you for your attention.